Welcome. Thank you for coming to this tutorial. I will talk about Banach Poisson-Lie groups. So this is supposed to be a tutorial, so it's really the basics of it. I will start on the blackboard for half of the talk, or half of the tutorial, and then I will switch to some slides. Okay? Let me start with the finite dimensional Poisson manifold, the definition. And then we will go to infinite dimension, and we will see some difficulties, some subtleties of the theory in this case. I will suppose that you are familiar with Banach spaces and with groups. So I will not, for instance, define adjoint, coadjoint actions. I think this is okay for this, this graph. I will maybe focus on what Poisson can mean. Okay? So for a finite dimensional manifold, in the finite dimensional case, I should write large, I think. So manifold. So what it is a manifold M, a manifold endowed with a bracket. And this bracket is defined on the space of smooth functions. So it takes two smooth functions on the whole manifold M and give us another smooth function. And it is such that it is antisymmetric. So F bracket with G is minus G bracket with F. It satisfied Jacobi identity. So you have a bracket of F with a bracket of G and H, where F, G, and H are functions, smooth function on the manifold. And you take a circular permutation, and this gives you 0. I hope I did it in the right way. H, F, G, like this. Should be 0. And the last identity is a Leibniz rule. If you pair a function f with a product of g and h, you will get the rule of the derivation. So you will get g bracket multiply as function with f and bracket of f and h plus h. The bracket of f and g. So these are the three conditions. Examples. Example 1, the dual space G star of a finite dimensional Lie algebra is a finite dimensional Poisson manifold. And here the bracket, and I will write it down because we will try to make sense of these in the infinite dimensional setting. So you have two functions, and these two functions are defined on the dual space of this Lie algebra with value in R. And if you take the bracket of two functions, you can evaluate it. It should be another function, another smooth function on a manifold, which is here the dual space of the Lie algebra. So you can look at the value of this function at a point mu, which is here in the dual space of the Lie algebra. And this value is simply the pairing of this mu, which is in the dual space, with the bracket of the derivative of the function f. F is supposed to be smooth, so it has a differential at mu with the differential of g at mu. But here we make an identification, and I hope I have some color. Yeah. Here what we do is the following. The differential of f is a function that's take a vector on in G star and give us a real number. So this is in fact an element of the dual of G star, so B dual of G. In the finite dimensional case, we make this identification G star star, the B dual, identify with G. And in G, we have a bracket because we take this Lie algebra G. And this is the bracket that we use here to pair the covector mu with this element of G. So I can add perhaps here. This is in G. And here we have the duality pairing between G star G. Okay. In this case, Hamiltonian vector fields, I will define what it is right now. Of course, this is the aim of this is to do some mechanics, for instance. So to each function, we get a vector field associated. So the vector field, in this case, associated to a function h, smooth function on M, is simply, and here I will use adjoint, coadjoint notation. You can see it here. If we look at how a function acts on other functions, well, it acts through its differential by coadjoint action on the G star. So we have the differential of the function at a point mu, this one, and it acts on the covector mu. Mu is again in G star. And this is then, in this case, an element of G star. So it gives us a vector field on G star. So let me stress here that this vector field is defined through its action on functions. So what we do is that we look at this action. I'll write it again because it has some consequences. This vector field, xh, is defined on the action on the differential of other functions. Here again, we take the pairing between G star and G. So we see immediately some problems that can occur in the infinite dimensional case. So here, for instance, to define this vector field, we define it through this action on differential of function. We will see that in the infinite dimensional case, perhaps the differential of function gives us a space which is too big, and we need to go to some other class of functions, some admissible functions. Then it is not clear that this space of differential will span a space which is big enough to define uniquely this vector field. This is one problem that may occur. Yes. We will need to think about what is a space that the differential of smooth function defined on the whole manifold is spanning. Let me go to another example of Poisson structure, of Poisson manifold, example 2, which are symplectic manifold. So here M is endowed with a closed 2 form, which is closed and non-degenerate. The non-degeneracy condition means that if you look at this 2 form, which usually takes 2 vectors of the manifold, and if you plug in 1 vector, then you go from the tangent space to its dual, simply by inner product. The non-degeneracy condition means that this fact is injective. In the finite dimensional case, injectivity implies surjectivity, and any covectors can be written like this, which will not, in general, be the case in the infinite dimensional setting. And then we can define a bracket, the associated Poisson bracket. Yeah.
Yeah, I'm not sure about music, but I thought usually it is omega flat and pi sharp.
Yeah, I'm okay with everything. I'm not a musician, so.
For the Poisson tensor is
also sharp for Poisson. Okay. So here I define the Poisson bracket of 2 functions. F and G are functions on the manifold, and we can pair this function using vector fields, which are defined like this. XF is defined uniquely, and XG defined by, and again we take like a duality pairing here, because we look at the differential, oh, I should keep the same notation, the differential of F, which will give us a covector, and this covector in this case can always be written like, in the finite dimensional case, can always be written like an inner product with some vectors using the symplectic form, and this is exactly the definition of XF. So the Hamiltonian vector fields here are again defined using duality. So if I write it explicitly, I can use this flat map and define it like the inverse image of the differential of the function through this flat map. Yes, and the non-degeneracy of W, of omega, sorry, makes it.
Is it possible to say the omega equal to 0 then?
Oh, yeah, sure. Yes. Okay. S. So here, yeah, perhaps I will. Yeah, perhaps I should write this. Here, if we want to write F and G, then we get this symplectic form applied to X, F, X, G, which is exactly df applied to xg. So this is a pairing between xg and df. Here the pairing is between the dual space of M to the tangent space. And we can write it also like P df dg, where perhaps I should write it like minus g minus dg applied to inverse image of omega flat of df. Try to keep the same notation like this. Yeah, so perhaps I have a sign here. So here there is a tensor P, and we will define it a bit later, which is the Poisson tensor in this case, which is actually exactly the inverse of the flat map of the symplectic form. Example for quadjoint orbits. So here, if we restrict the first example to an orbit of the group, we get a symplectic manifold with this symplectic form called Kerrellan-Kostov symplectic form. Example, I can say example 3, quadjoint orbits. So this is an orbit of an element of mu of G star. Sorry, G star is a dual space of the Lie algebra, and we look at the adjoint action of the group G. G is a Lie group associated to the Lie algebra G. And in this case, the Poisson structure that I have defined in the first example restricts to a symplectic form. And more precisely, if we look at tangent vectors at mu is a covector, generated by two elements of the Lie algebra by infinitesimal action, then the symplectic form is simply the restriction of the Poisson structure that I have written over there. So the pairing between mu and the bracket of A and B, where A and B are in the Lie algebra. And mu here is in the dual space. Okay, so these are the three examples I wanted to mention. So let me make a list of difficulties in the infinite dimensional setting. Okay. I don't know if I will go to the slides, but it's not a problem because there is another talk about this topic tomorrow. List of difficulties in infinite dimensions. First of all, when we start with a covector, let me call it Xi, on a Banach manifold M covector, it is not clear that there is a smooth function defined on the whole manifold M, which has as differential exactly this vector at this point. The question is the following: is there a smooth function f on the whole manifold M whose differential at mu, I should perhaps call it M because it's at M, at small m, equals this covector. And the difficulties come from the fact that we may not have bump function to localize. So related to the existence or non-existence of bump functions. So even, and this is also related to the fact that the differential of smooth function defined on the whole manifold, in the case where we cannot localize, may not span the whole dual that we take as a dual of a Banach space. So the differential of smooth functions may not span the dual space of the tangent space at M. So this is in the case where we cannot make use of bump function to localize. Yeah.
To have these functions globally defined or locally?
I'm talking here about globally defined, and that's the point, yeah.
Because you can use
locally, we can always do it.
Yeah.
Yes, yes. So there's one approach is Poisson geometry is to use globally defined function, which was the case in the definition. The finite dimension definition is a bracket on the space of functions which are globally defined. But as you see, it leads to difficulties. Let me also mention that the Leibniz rule in the infinite dimensional case does not imply the existence of a Poisson tensor. Poisson tensor like this one, in this case, does not imply existence of a Poisson tensor, and this we cannot avoid. This is, even on a Hilbert space, there are Poisson brackets that are not defined by Poisson tensor. And this is related to the fact that there exists, so perhaps I should say what the Poisson tensor is. If you have a bracket, the Poisson tensor is a tensor that eats the two differentials. So this may not exist, and it is related to the fact that there are queer tangent vectors. And these were queer tangent vectors were introduced by Kriegel and Micho. Existence. So these are operational tangent vectors. Let me stress that this is a diversity-friendly word. Tangent vectors. create a tangent vector, we can define Poisson bracket that eats functions, but use second derivative of the function, not only the first one. So this is these are now called here Poisson brackets. And the reference is a paper that we published with Daniel and Thomas. And I have two more lists of difficulties, and I'm running out of time. But that's fine. Perhaps I will just mention the third difficulty is localizability. The Poisson bracket may not be localizable. And it is related with what I just stressed before. Localizability. So is the bracket using the jet of the function or something else? Is it local or not? And again, if we don't have bump function, we cannot, not sure of this. And for so existence of Hamiltonian vector field may lead to problems. So existence of Hamiltonian vector field, not guaranteed. And the last difficulty I can mention, I mentioned this Jacobi identity here. In the finite dimensional case, you can write it in terms of differential of f, differential of g, and differential of h. And it turns out that in the finite dimensional case, the right-hand side of this identity is a tensor. So you can relate the vanishing of this identity to a vanishing of some tensor. It is not clear in the infinite dimensional case that the right-hand side is tensor. Okay. I have one result where I know it is a tensor. It is on groups, and yeah, I cannot mention it here, but I don't know how to do it in the general case. For the last 30 seconds that I have, I will just make an advertisement because yes, please. I want the screen, and I will just advertise one paper where we compare different approaches to Poisson geometry, because from now, I just give you the definition in the finite dimensional case. I wanted to stress some difficulties, and there are many different ways to go around these difficulties, and it depends mainly on the applications. So in the paper it's a recent paper from December with Thomas and Praful, we took the different approaches that were in the literature on Poisson geometry and the definitions, and we compared them. So mainly there are three different ways to approach this, either by an anchor map, the T sharp in this case, which goes from T star M to Tm, or a sub-bundle of T star M to Tm. This would be the, let me see, so these are the usual definition in infinity, but perhaps I should stress this approach by Cabot and Pelletier through the Poisson structure defined as using a bundle map, E, so this is an anchor map. We were mentioning yesterday that there are many different terminologies. Aneta mentioned that this topic is not yet settled, and indeed. So I can mention perhaps this definition of Cabot-Pelletier through anchor map. Then there is another approach using Poisson subalgebra. So Poisson subalgebra of the algebra of smooth functions. So we restrict the functions that are that we will be able to bracket. So this is then the second approach you can see in this paper that we define, or we give the definition of all this. So this is more the approach of Nib, Salman, and Thiemann, where we ask for a Poisson bracket defined on a sub algebra of smooth function defined on the whole manifold. And the last approach, which is the one that I used for in my paper on Banach Poisson-Lie group in relation to KdV equation, simply through section, so using a Poisson tensor section of an appropriate subbundle. So simply defining what should a Poisson tensor be. So this is another approach which was actually adapted to the projective case in October 24 by Lee and Wang. So here, after you see another definition, 27, about Poisson. And I will advertise this paper because at the end, we make a comparison, and you see there are some difficulties, and each approach has its advantages and disadvantages. So let me show you so here there is a list of differences between the different approaches, where the Jacob identity is satisfied. If there is a Poisson tensor, if it's possible that there's no Poisson tensor, if the Poisson bracket is necessarily localized when this definition is taken. And at the end, you have a table to compare. And you see here are listed 1, 2, 3, 4, 5, 6 definitions. And so, yeah, each definition has these advantages. And I should stress here that when we write a check, this means that this property is implied by the definition. When there's nothing, this means simply that it's not implied. And it's not bad or wrong, it's not bad or good, because in some cases we want more flexibility. So it's really depending on the application. For instance, in my case, the last two definitions are more or less the same kind. I don't assume that the existence of Hamiltonian vector fields, because in the example I wanted to have, I was not sure that the Hamiltonian vector field will exist. And indeed, in this paper, we have an example in operator theory where there's no Hamiltonian vector field. Yes, but in my case, I have subbundles of smooth subbundles. In other definition by Cabot and Pelletier and by and collaborators, the definition makes sense on co-distribution, so some distribution of the cotangent bundle, which may not be smooth. And this may also make sense in some cases. Okay, so I think I will finish here. I have some slides about Poisson. So perhaps I should say what a Poisson-Lie group is. It's a Poisson manifold with a group structure. Both are compatible. Thank you very much for your attention.